Hi, this is Emma Horwitz, and this is my Khan Academy video on free energy and thermodynamics, number 19.5, solving delta G under standard and non-standard conditions. Problem number 19.5 says, consider the following reaction. 2 nitrogen dioxide gas in equilibrium with dinitrogen tetraoxide gas. A, using the thermodynamic data in the appendix of the textbook, calculate delta G naught at 298 Kelvin. Then B says, calculate delta G at 298 Kelvin if the partial pressures of NO2 and N2O4 are 0.40 atmosphere and 1.60 atmosphere respectively, and therefore not under standard conditions. The variables and values we are given in the problem are temperature equals 298 Kelvin, the partial pressure of NO2 is 0.40 atmosphere, and the partial pressure of N2O4 is 1.6 atmosphere. And then from the textbook, we can find that the delta G of formation of NO2 gas is positive 51.3 kilojoules per mole, and the delta G of formation of N2O4 gas is positive 99.8 kilojoules per mole, both of those under standard conditions. The equations we will be using are first the reaction equation to NO2 gas in equilibrium with N2O4 gas. Then we will use the equation for delta G naught of the reaction, which equals the sum of the number of moles of products times the delta G of formation of the products, minus the sum of the number of moles of reactants times the delta G of formation of the reactants. The last equation we'll be using is delta G under non-standard conditions equals delta G naught plus RT ln Q, where R is the gas constant, which is 8.314 joules per Kelvin mole, T is 298 Kelvin, and Q is the partial pressure of N2O4 raised to the number of moles divided by the partial pressure of NO2 raised to its number of moles. So for 19.5a, we are going to begin by inserting delta G's of formation and number of moles for the products and reactants into the first equation. So we have delta G naught equals 1 mole of N2O4 times 99.8 kilojoules per mole minus 2 moles of NO2 times 51.3 kilojoules per mole, where the moles cancel out. Then you simplify the equation and you end up with delta G naught equals negative 2.8 kilojoules. Then for 19.5b, we begin by solving for Q, where we take this equation, the partial pressures raised to their mole numbers divided by the partial pressure of the reactants raised to its number of moles. You plug in those values, 1.6 atmosphere and 0.40 atmosphere, and you get that Q equals 10. Q does not have any units, so it's just 10. Then you're going to insert values into this last equation, delta G of reaction equals delta G naught plus RT ln Q, using the delta G naught of reaction that you found from 19.5a. So you get negative 2.8 kilojoules plus 8.314 joules per Kelvin mole, but you need to convert that into kilojoules because delta G is in kilojoules. So you multiply that by 1 kilojoule divided by 1,000 joules. Then you multiply that as well by 298 Kelvin, which is T, and ln of 10, which is Q. You simplify these, and eventually you end up with positive 2.9 kilojoules for delta G of reaction under non-standard conditions. A summary of what we just did is that in 19.5a, we used the delta G's of formation for the products and reactants to solve for delta G naught of the reaction, where we got negative 2.8 kilojoules. And for the second part, part B, we used our answer from A and the variables R, T, and Q to solve for delta G under non-standard conditions. And for that, we got positive 2.9 kilojoules. Thanks for watching.